Today we will examine the idea of a limit somewhat more carefully. So what is a limit? Well, let's let a and L be real numbers, and we say that the lim as x goes to a of f of x equals L, if whenever x approaches a but does not equal a, f of x approaches L. And what we mean here is that as x gets closer and closer to a, f of x gets arbitrarily close to L and to no other real number. And what we mean here is f of x must get as close as anybody can imagine and then some to L, and there can be no other real number with that property. So if there is a limit, it's unique. And it's also important to note that this has to work both when x is less than a and when x is bigger than a. It's important to note that we do not allow x to be a during this limit process. And one of the reasons why this is important is if you remember when we calculated the slope of the tangent line to y equals x squared at 1, 1, we ended up with a limit that looked like this. Okay? If you let x equal 1, then this whole mess becomes undefined. You have to do it with this limit process. So x gets close to 1, but x is never allowed to equal 1. So let's take a look at the following example, the limit as x goes to 2 of 3x minus x squared. And what we're going to do is we're going to take some x values near 2, and we're going to calculate the value of this and see what happens. Okay, so we start at 2.1, which is a little bigger, and 3x minus x squared is 3 times 2.1 minus 2.1 squared. You go through the algebra, you get 1.89. And we're going to do this for all sorts of values closer and closer to 2, and they're reflected in this table. You can see when we go from 2.1 to 2.01 to 2.001, 2.0001, closer and closer to 2, these values that appear over here on the right-hand side are getting closer and closer to 2. Now remember that we said this has to be true whether x is bigger than 2 or x is less than 2. So we start with some things less than 2, 1.9. We calculate and get 2.09. And we continue along, 1.99, 1.999, 1.9999. And what you can see is on the right-hand side, these values get closer and closer to 2. So no matter whether we come in from values bigger or from values smaller, we're getting numbers that look closer and closer to 2. So we believe that the limit is actually 2. This probably shouldn't surprise you, because if you were thinking about this and you're thinking, okay, so x is getting close to 2, 3 times x should then be getting close to 3 times 2 or 6. X squared should be getting close to 2 squared, which is 4. 6 minus 4 is 2. Yeah, what a surprise. If we look at the graph, we can see what's happening as well. So if we have some values of x that are slightly larger than 2, the function value up here is slightly less than 2, which we can see across here on the y-axis. When we move in towards 2, we're sliding up these curve, and the function values are sliding up towards 2. Now, when x is less than 2, what we can see is when we slide up to the curve, we got function values that are a little bigger than 2 as we slide across here. When you move in close to 2, we're moving down the curve here, and the values we're going to see over here are moving down to 2, which is exactly what we saw in our table. Now we look at the following limit. Our intuition doesn't get us very far here, because you think to yourself, okay, so x is getting close to 1. X minus 1 must be getting close to 0. Square root of x must be getting close to the square root of 1, which is 1. 1 minus 1 is 0. So this thing is getting close to 0 over 0, which tells us nothing. So here we need to really calculate. Okay, and at 1.1, And here we need a calculator to do this because obviously I did not get this number in my head. But you do the calculation and you get at 1.1 that this thing is 0.488, da 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 da. So we go through this with values closer and closer to 1. 1.1 got us that. 1.01 gets us this, da 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 da. And what you can see here is as we move from 1.1 down towards 1, these function values are getting closer and closer to 0.5. When we go the other direction, we start at 0.9. We move up to 0.99, 0.999, 0.9999. We can see that these values are coming down towards 0.5. So it looks like from either direction we're headed towards 0.5, and that's what we think the limit is. Now if we look at the graph, we're going to see exactly the same sort of behavior here. Notice incidentally, in this function, it's not defined when x equals 1. Okay, but it doesn't matter because in the limiting process, x is not allowed to be 1. So here we start with a value slightly larger than 1. You can see we go up to the graph, we come across, we've got a function value slightly less than 0.5. As we move this direction, we move along the curve. These values go up towards 0.5. Same story from the other side. Okay, we've got function values that are a little bigger than 0.5. When we move this direction, we move up to the curve, we go this direction, and our function values are going to come down to 0.5, which is what our limit is. Now let's take a look at a somewhat more complicated function which is defined in a piecewise manner. We want to look at the limit as x goes to 1 of f of x, where f of x is x squared when x is less than 1, and 3 minus x when x is greater than or equal to 1. When we use x values slightly larger than 1, we end up using the definition 3 minus x, and when x is 1.1, 3 minus x is 3 minus 1.1 or 1.9. When x is less than 1, say 0.9, x squared is going to be 0.9 squared, which is 0.81, and we can already see those two numbers are not very close to each other. When we complete an entire table here, when we start at 1.1 and move downwards towards 1, we can see the values that we're producing are moving upwards, and they look like they're going to 2. On the other side, when we start with an x value of 0.9 and we move upwards towards 1, 0.99, 0.999, 0.999, the function values appear now to be headed to 1. Okay, so from the positive side, it looks like the function values are headed to 2. From the negative side, it looks like the function values are headed to 1. That's not one real number. This limit doesn't exist. However, we'd sort of like to capture the fact that the limit's trying to exist. It's just giving you different answers from different sides. And the symbols we're going to use for that are the following. The lim as x goes to 1 plus, which are numbers above 1, is 2. And the lim as x goes to 1 minus of f of x, and these are numbers less than 1, is 1. And these things are called one-sided limits. The lim as x goes to a plus of f of x is defined exactly the same way the limit as x goes to a is defined, except that x is going to be bigger than a throughout the limit process. We don't allow x values less than a, and the lim as x goes to a minus of f of x is defined in a similar fashion. Now, however, x is only allowed to be less than a through the limit process. So bigger than a, x goes to a plus, less than a, x goes to a minus. And now if we look at our graph, we can see what's going on here. If x is slightly bigger than 1, the function values are up here. They're a little less than 2. And as we move this direction, we slide up this curve, and the function values slide up the axis towards 2. When we're a little less than 1, and we move towards 1, we can see that the function values are going to slide up this curve and give us a limit of 1 if we stay on this side. So these are called one-sided limits. On this side, x bigger than 1, the function values heads towards 2. On this side, x less than 1, the function values head towards 1. We now consider the function x plus 2 over x minus 1, and we look at the limit as x goes to 1 plus, and we look at the limit as x goes to 1 minus. We do our standard calculations. At x equals 1.1, x plus 2 over x minus 1 is 31. And at x equals 0.9, x plus 2 over x minus 1 is minus 29. Those numbers are nowhere near each other, but things actually get worse as we look at our table. As x approaches 1 from above, higher numbers, 1.1, 1.01, 1.001, etc., we get outputs of 31, 301, 3001, 30,001. And when we approach minus 1 from below, smaller numbers, we get minus 29, minus 299, minus 2999, minus 29999. So what appears to be happening here is that when we come in to 1 from numbers bigger than 1, we get huge positive numbers, and when we come in to 1 from numbers below that, we get huge negative numbers. And that means that both of these one-sided limits do not exist. When we look at the graph, we can see what's happening. When we have values of x that are larger than 1, we find ourselves on this top curve up here. And as we approach 1, the values run up this curve and become huge and positive. When we're on the other side here, we find ourselves down on the lower curve, and as we approach 1, we run down the curve and we get huge negative numbers. And in fact, if you look at this graph, you can see that there's actually an asymptote here. We'd like to be able to indicate that, and the way we're going to do that is writing the lim as x goes to 1 plus of x plus 2 over x minus 1 is plus infinity, and indicating we get huge positive numbers this way, and the lim as x goes to 1 minus of x plus 2 over x minus 1 is minus infinity, indicating that we're running down our asymptote. Okay, it's important to note that if we write the lim as x goes to a plus of f of a equals plus infinity, we're not describing the value of the limit. We're describing how that limit does not exist in a very special way, namely things get huge and positive. And the same idea with negative infinity, which means that the values are going to become huge and negative. Now, without the graph, how can we compute this? Well, let's look at the lim as x goes to 1 plus of x plus 2 over x minus 1. If you look at the top, x is getting close to 1, so x plus 2 is getting close to 3. X is getting close to 1, so x minus 1 is getting close to 0. But what's important down here is x is a little bigger than 1, which means that x minus 1 is a little bigger than 0. So the things on the bottom are positive and very close to 0. You take a positive number, divide it by a very small positive number, you get a huge positive number, and that's what the plus infinity indicates here. When we look at the limit as x goes to 1 minus, we do a similar calculation. The top still looks like 3, but now the bottom looks like a negative number because x is a little less than 1, so x minus 1 is a little less than 0. 3 divided by a negative number is negative, and 3 divided by something close to 0 is really big in magnitude, which means that we get minus infinity.